Hello, and this is the first of two videos covering limits and derivatives. In this first part video, I'll first define what a limit is, and I'll give some examples of functions that have um, a limit and those that do not have limits. I also like to talk about a limit of the determinate form as well as in the indeterminate form. That is a limit involving a function that at the limit the denominator is 0. That's the indeterminate form. And then I'll talk about a derivative as a limit. So this is a review of what you first learned in calculus, and we'll look at how to calculate a derivative as a limit. So after taking notes on this lecture and doing the relevant problem sets, the objective for you is for you to be able to understand what a limit is and how to solve for the determinate form. At least that's the topic of this video. So let's define a limit here, and I'm going to do it somewhat informally. So if we describe a limit of a function as x approaches some arbitrary value, in this case a, and we'll write our function f of x, is equal to L, that means that as x approaches a, f of x approaches L. So for example, we may have a function that, some arbitrary function, and as the x value, or as x approaches our value a, then the function approaches the value L. And this is different than a statement that f of a is equal to L, because f of a may not exist, as I've drawn in this picture. Right? So in this arbitrary function, I've shown that it's a function that doesn't really exist at the value of a, but it approaches this value L at x is equal to a. So let's consider an example. Let's consider the example of as x approaches 2, let's look at what 3x plus 4 approaches. And this is a relatively simple limit because you can see, well, this is a continuous function, and f of 2 does exist, and the answer is of course simply 10. Another example is the limit as x approaches 0 of x cosine x, and that too is somewhat trivial to compute because this is a continuous function of x, and that is equal, well, the cosine part gives a 1, but as x goes to 0, the whole function goes to 0. So these are some relatively simple examples, and I've mentioned a couple of times in these two examples that the functions are continuous, but let me just define what that means. So a function is continuous at point x equals a if the limit of as x approaches a of that function is equal to f of a. That is, f of a exists. And f of a must exist, and the limit of f of x has to approach f of a. And just here's an example of a discontinuous function. Right here, as x approaches a, the limit of the function differs from f of a. Okay, so that's just an example of a discontinuous function. So these are two examples of determinate forms of limits in which the limits exist. Let's look at some examples of limits that don't exist. So these are functions with limits that do not exist. So one of which is the limit as x approaches 0 of x over the absolute value of x. So we can sketch that, for example. So when x is positive, then x over the absolute value of x is equal to 1, right? So this is 1. And when x is negative, x over the absolute value of x is equal to minus 1. Right? But as x approaches 0, we approach this region where the function is not defined. Another example is the limit as x goes to 0 of 1 over x. Right? And that looks like something like this. And again, as x approaches 0, 0 being right here, the function is not defined. And then, well, likewise, another function that doesn't have a limit is the limit as x goes to 0 of 1 over x squared. And that is always positive. Draw it with my white pen there. It's always positive, but again, as x approaches 0, there is no limit. Okay, so those are some examples of limits that do exist and some examples of limits that do not exist. Let's talk about some behaviors of limits, or rules of limits, I guess. So, for example, if let's consider the limit as x approaches a of f of x. Let's say that's equal to L, and the limit as x approaches a of a different function of x, g of x, and let's just say that has a limit of m. So the first rule of limits is that the limit of f of x plus g of x is simply equal to the sum of the two limits, L plus m. Another rule is that the limit of the product of f of x, g of x, is equal to the product of the two limits. So it's the limit of f and the limit times the limit of g. I suppose this definition is perhaps something that you might expect, but I'm just going over these for a bit of formality. Mathematics is a language. We have operations that have rules, and these are the rules of limits. And we can also take the limit of the quotient of the two functions. And that's also equal to the quotient of the two limits. Right, the limit of the quotient of the two functions is equal to the quotient of the two limits. And this is true, again, if m is not equal to 0. Okay, so now let's talk about the indeterminate form. So the indeterminate form would be if m is equal to 0. So an example of a limit with an indeterminate form is the limit of, as x approaches a, of f of x over g of x. And again, we call that the ratio of the two limits. And the indeterminate form is represented by the situation in which the limit of the denominator is equal to 0. So this becomes a bit of a challenge when that's the case. So for example, let's look at the limit as x approaches 1 of x squared plus 1 over x minus 1. Right? We can see that the limit of the denominator is 0. But we can solve this if we do some algebra in the situation where x is close to but not equal to 1. So we're going to assume that x is close to but not equal to 1. Okay, right? So if we do that, we can oops, and I'm noticing I made a little mistake on my numerator equation here. Let's use the function x squared minus 1. Okay, so we can break the numerator into the product of two functions, x plus 1 times x minus 1, and divide that by the denominator. And this becomes, when x is not equal to 1, but is close to 1, then the function is very close to, well, it's x plus 1. So the limit as x goes to 1 of our function is equal to 2. Okay. Another example, let's consider the limit as x goes to 0 of x squared over x. Right? When x is equal to 0, then we can evaluate this quotient. Right? but we can, if x is close to but not equal to 0, we can carry out the algebra and just say that x squared over x is equal to x. So the limit is x squared over x, or sorry, the limit as x goes to 0 of x squared over x is equal to the limit of x, and that's equal to 0. And you might understand that in the sense that as x becomes very small, x squared becomes smaller more rapidly than x. So that's why as x approaches 0, the limit is equal to 0. Now what about this case? Another case. Let's consider the limit as x approaches 0 of sine x over x. Okay, so this is a situation where simple algebra won't work. But let's do a little bit of manipulation. And so we can subtract 0 from both the numerator and the denominator. Right, because so we'll subtract sine of 0, which is 0, from the numerator, and we'll subtract 0 from the denominator. And by doing that, we can see that that gives us the limit as x delta x approaches 0 of sine of x plus delta x minus sine of x all over delta x. That is, if we evaluate that function at x equals 0. Okay? And you might recognize this limit as the definition of a derivative. That is, the derivative of a function, which we can write as df dx, or just f prime, is equal to the limit as a change in x goes to 0 of f evaluated at x plus delta x minus f evaluated directly at point x all over delta x. And this is the definition of the derivative of a derivative. Okay, so knowing that, we can now evaluate our original limit of sine x over x if we know how to take a derivative. And well, you do, because you've taken calculus, but the derivative of sine x dx is equal to cosine x, and we're evaluating it at x is equal to 0, right? As we showed that this limit has to be equal to the derivative evaluated at x equals 0, and the cosine of 0 is equal to 1. So we've solved this indeterminate form of a limit using the definition of a derivative. So let's talk a little bit about how we can interpret a derivative. And the first way you were probably introduced to this is by understanding a derivative in terms of the slope of a function evaluated at a certain point. So here I'm drawing an arbitrary function on my x and y axis. And let's say we want to evaluate the derivative at point x. So we look at the function evaluated at point x, and we compare it to the value of the function evaluated a small distance from that point, delta x. Right? So this is the function evaluated at x plus delta x, the right side point, and the left side point is the function evaluated at x. So we take the difference between those two, and so the difference between the two functions is the rise, and the run is delta x. So we have a slope f prime at point x is the slope, or the slope of the tangent line at point x. Or we can also write f prime, or the derivative of f, is equal to the limit as delta x goes to 0 of delta f at point x divided by delta x. So let's look at the function f of x is equal to 2x squared plus 3x. So let's evaluate f prime. So f prime of x, again, is equal to the limit as delta x approaches 0 of 2x plus delta x squared, right? So we're evaluating the function at x plus delta x plus 3x plus delta x, and we have to subtract the function evaluated at point x divided by delta x, and that equals 2x squared plus 4x delta x plus 2 delta x squared plus 3x plus 3 delta x minus 2x squared minus 3x all over delta x. And you'll notice we can cancel out the terms that are not products of delta x. And this gives us the limit as delta x goes to 0. We have 4x delta x over delta x is just 4x plus 2 delta x squared over delta x is just delta x plus 3 delta x over delta x is just 3. And you can see that as delta x goes to 0, that function approaches 4x plus 3. And so that's how we can evaluate the derivative using our knowledge of limits. So I'm going to conclude this video. Again, we've defined what limits are. We've looked at functions with and without limits. We've learned how to solve the determinate form of a limit, and we've also looked at the indeterminate form and understood how to solve those forms using the derivative as a limit itself.